I did not get to. I didn't contribute. Like it's my own fault. I'm the only like scholarship but it happened because it sound like there were people do you want to not to that's just and then I it was 11 people. I mean I don't think I stopped and so I did like I read my book and I did my online conversation. I was like whatever. I did watch the wait, you see it on yesterday. And I'm just gonna watch the video because I know that I've already done. Yeah, you know, if the questions really good, I watch this. I just no, I said I'm not like I'm understanding now. Yeah, it's just not. Yeah, did you watch the videos last night? It's okay. But we actually and I think I will make it. Yeah, but it's mandatory. Yeah. Yeah, I have what I don't really. I have no idea. It's clicking by anyone that required this yeah. So I would love. So I was like combined, bunch, and then this essay once. I did like a 7-day free trial, and it's like scholarship shit, and I've now push myself to as many essays. I have to find this 7 days because I don't want to the money. Against one, yeah. I have my one from yesterday. I didn't show you almost yesterday.
Yeah.
It's just, I remember, you know, the different ways and stuff, like, oh, it's pretty fun. And they're like, yeah, so, now that's what the time, but two points, like, oh my God, it's so hard. You know.
It's awful. So yeah. Switch it out. Should I just go now?
Yeah.
You don't do it. You do. Yeah.
Yeah, you do.
I can bring it. Yeah. It's what's not the same. Like, there's either it's either gonna get taxes or it's gonna get. Yeah. I got one. I know. Yeah. I know. That's horrible. Like Saturday. And what stinks is I have a tongue honest. So it's like I'm sitting in North Carolina.
Yeah.
Like,
Yeah.
I think we'll find out. Around Thursday, whether it'll be. That's if I do any exhibitions. Not what anybody else is.
Yeah.
Like the houses in North Carolina are getting like.
Okay, so our quiz is tomorrow, but we're going to start our notes from 5.1. Okay, so let's go to page 1 in your new packet. So this unit, we're talking about, falls under the category of curve sketching. So we're concerned about using derivatives to help us get an idea how the shape of the graph looks and properties about the graph related to slope and concavity. So today, we're talking about extreme value theorem, which is basically, can we find the peaks? Can we find the highest and lowest points on the graph relying on just a few sets of information and not relying on the picture of the graph? So there's some definitions, though, I want to go over with you. So extrema is plural for maximums and minimums. And max and mins can fall into two categories. It can be either an absolute maximum or it could be a relative maximum or minimum. So a relative minimum, a relative max and relative min are basically hills and valleys of a graph. So here, this point will be a relative maximum. This point will be a relative minimum, and this point will be a relative maximum as well. The reason that we call it relative, or sometimes you may see local maximum, is because it is relative to the immediate points around it. It is higher than those points, okay? And here it is called a relative minimum because if we compare points directly closest to that point there, it is lower than those points. So as long as a point is higher than the points on either side of it, then we can call it a relative maximum. As long as that point is lower than the points immediately to the left and to the right, we call it a relative minimum. Here, this is also a relative maximum. But this also falls under the category of an absolute maximum because there's nowhere else on the graph that is higher than this point. So this is called the absolute maximum because over the entirety of the graph, that is the highest point. This graph has no absolute minimum because you would say maybe absolute minimum is negative infinity. But if we're talking about absolute max or absolute min, it has to be a physical point on the graph. And negative infinity is not a physical point. So this graph would have no absolute minimum. This is an open interval because the graph has no beginning and no end. This graph would be a closed interval because it has a beginning and it has an end, and both points are defined. Both endpoints are defined. This graph has a relative minimum because it has a valley of the graph, but this is also an absolute minimum because there's no place else on the graph that's lower than this point. This point here is an absolute maximum because it's the highest point over the entirety of the graph. But this is not a relative max. Because even though this point is higher than the point to the left, it is not higher. There's no point to compare on the other side. So this is not a hill of a graph. It does not hill of a graph is not considered a relative maximum. So basically, endpoints can never be a relative maximum or a relative minimum. Right, so again, relative or local extremas are hills and valleys of a graph, and absolute extrema are the highest or lowest points over the entirety of the graph. Poles and infinity, plus or minus infinity, are not considered to be absolute extrema. Right, an open interval would be a graph that looks like this, where I meant to have us show that there are holes at the ends here. So this graph still has a relative minimum. It still has an absolute minimum, but this graph has no absolute maximum, even though we see that there is an endpoint that the graph is never going to be higher than that hole, that y value of that hole. The reason why there is no absolute maximum is because if you pick a point really, really close to the hole, you can always come back and pick a point even closer to it. So we're not able to pinpoint a specific y value that's the highest because we can always inch closer and closer towards that hole. So we can't pinpoint a specific number. So therefore, this graph has no absolute maximum. Right, so today we're talking about extreme value theorem, which is basically, I'll read this here. If a function is continuous on a closed interval, so we've seen that before, right? With intermediate value theorem, we have to establish that the graph is continuous, that there are no breaks, that there are no asymptotes, that there are no holes. And I took off points in unit 1 when if you didn't say that the graph is not, if the graph is continuous. So we have a couple of theorems coming up, and all the theorems require this statement of continuity. So we want to make sure that anytime that there's a theorem involved, we have to establish function is continuous on the closed interval. It doesn't mean that you have to do a whole bunch of checks. There are certain things that gives it away. If it's a polynomial, you know that there are no breaks in the graph. You can just go ahead and state the function is continuous on that closed interval. So if a function is connected, then it has both an absolute minimum and an absolute maximum on that interval. The only exception is a constant graph or a constant function. If I had just a horizontal line, then yes, there would be no maximum, no minimum. But if it's any other scenario, as long as the graph is continuous, if it's a curve or if it's a linear graph, then we're always going to be able to identify an absolute max and absolute min on that graph. So here are how we're going to identify those absolute max and absolute min. The absolute extrema will be either at a critical value or at an endpoint. Right? So critical value is basically where the derivative of the graph is either 0 or undefined. Right? Either where the slope is 0 or the slope is undefined. So here is an example of where we look for our candidates for absolute max and absolute min. So for instance, if I had a graph that looked like this, the only candidates I have to worry about in terms of the potential highest or lowest points on the graph are the endpoints. So we always have to consider the endpoints because we can imagine that the endpoints can stretch in a way where it could end up being the highest or lowest points on the graph. We also have to consider wherever the slope is 0. Wherever the slope is 0, it could be a place where a hill or valley of the graph, and we know hills and valleys of the graph could end up being the highest overall point. And we also have to consider places where the slope is undefined. So slope is undefined, like a sharp turn, because a sharp turn could end up being a hill or a valley of the graph, and that is also a potential candidate. So the way we look for a slope 0 is we would set the numerator of the derivative equal to 0. Sometimes there is no denominator. So really, if there's no denominator, then you're just setting the derivative equal to 0. If you want to look for a sharp turn, we always have to consider the denominator as well. So we need to set the denominator of the derivative equal to 0. Not every derivative will have a denominator, but if there is a denominator, if there's a variable in the denominator, we have to make sure we consider that as a potential candidate. Because if there's a sharp turn, if there's a sharp point, and if we don't consider it, we may miss out on where the actual absolute max or absolute min is. There's no other candidates to consider. There's no other points in between that could end up being the highest or lowest points. So we only have to consider the endpoints and the critical points. And critical points are going to come from your derivative function. Max and mins refer to y values at that point. We're going to present our answers in a way where I can stress that and that we can just focus on just the y values. We don't want to do order pairs. We don't want to do just x values. We want to do just y values. Okay, next page. Okay, so here are the steps that we're going to apply. We want to first confirm that our graph is continuous on the closed interval. So if there's a vertical asymptote, we may identify the location of that asymptote, but it may not cause an issue as long as it doesn't affect our interval, right? So we only care about the interval. We only care about if the graph is connected on that interval. If there is a break outside the interval, we can still continue with our theorem. So we want to confirm continuity. Next step, find critical points. They will always provide us endpoints, so you never have to guess where the endpoints are. So the way we find critical points, we find f prime, and if there's a denominator, then we set both the numerator and the denominator equal to 0. Identify all our valid critical points, and then we take our critical points and endpoints, insert them into the original function, and then we just compare the y values. Highest y value will be your absolute maximum. Lowest y value will be your absolute minimum. Okay, so let's look at example 1. So, obviously, if you have the graph in front of you, then it's easy. You can say, okay, that's obviously the highest point, that's the lowest point. We're doing this with minimal information, and we're just relying on endpoints and critical points to help us make our conclusion. All right, so we have a function 3x to the 4th minus 4x cubed. What is the absolute extrema? So we want to use EVT, which is my abbreviation for extreme value theorem. First thing is, do we have to worry about any breaks in the graph? Is the function continuous on the closed interval? Yes, right. It's a polynomial. There are no variables in the denominator. There's no square roots. Okay, but we have to make sure we state it every time that we're trying to find absolute max, absolute min. So this is the way you're going to state it. F of x is continuous. And I want you to specify the interval as well. It may be continuous everywhere, but this is to stress that we're only concerned about continuity on the closed interval. Okay, we have 2 endpoints, so that's fine. We know at the end, we're going to be using testing endpoints. There are going to be potential candidates. But let's go ahead and see if we can find any critical points. So critical points, we're going to find f prime and look for slope zeros. There's not going to be any slope undefined since we have a polynomial. It's a smooth curve all the way through. So we want to look for slope zeros because slope zeros could end up being a hill or valley of the graph. What's f prime going to be? Power rule. First term becomes what?
12x.
12x cubed minus, okay. And to find critical points, we always set our derivative equal to what? 0, yeah. So I see a GCF that I can factor out. I can factor out a 12x squared. That leaves me with x minus 1. Okay. I have my derivative in factored form. I can set both parts equal to 0. Solve for x. I get 0 and I get 1. So are we going to always use every critical point as test numbers? Can you imagine a situation where we may not use the critical point as part of our candidate? Or let me ask you this, where do the critical points have to be in order for it to be valid? Has to be where? Between, yeah, so between the endpoints. So keep in mind that we only care about the interval. So anything outside the interval is outside our problem, and we don't want to consider that. So you can imagine sometimes critical points may not fall inside the interval at all. And if it doesn't, if we don't find any critical points, we still move forward with extreme value theorem. We just have less candidates to worry about. So I don't want us to feel like, oh, no critical points. Okay, extreme value theorem breaks down. It just means that we don't have any candidates except endpoints, but we'll always have endpoints to consider. So here, 0 is a duplicate of 0. We were already going to test 0 anyways, so we can ignore that because that's 0, so it's going to be a duplicate. Is 1 going to be a valid critical number? Yes, okay. It falls between 0 and 2. So we have 3 numbers to test. We have 2 endpoints, and we have an additional critical point. And the way we test them is we're going to plug them all into the original function. Now we're trying to figure out where the locations are, y value-wise. And we'll compare the locations. Highest would be the absolute max, lowest would be the absolute min. So they all get inserted into the original function. So 0 into the function, I get 0 minus 0, which is 0. I plug 1 into the function. 3 minus 4, that's negative 1. I plug 2 into the function. I get 3 times 16, 18. Sorry, 48 minus 32, which is 16. And then looking at the y values, we can see what is the highest. So what's the highest number that you see? Absolute max would be what? 16. And absolute min would be negative 1. Okay. We only care about the y values. So we don't care about the x values. We don't want to say order pairs. We just want to specify just the y value. So we're going to say absolute max value is 16. Absolute min value, minimum value, is negative 1. So this is what College Board is looking for. If they ask for absolute max value, you may think, oh, wait, maybe it's the full order pair, 2, 16. It's asking for the y value. So it's a little bit cryptic. I know sometimes College Board, you wish they would say, oh, give us the absolute max y value, but they would just say maximum value. What's the absolute maximum value? We have to understand that as referring to the y value. Okay, number 2. F of x equals x minus 1 to the 1/3. My intervals from -1 to 0. There's a cube root, so cube root is not going to affect anything. There's no restrictions in terms of positive or negative numbers. So our function is continuous. There's no issues here. Okay, we already know we have 2 endpoints that we're going to plug in. We'll save that for the end. Let's go ahead and find any valid critical points. So critical points, we have to find the derivative, but to find the derivative, what rule do we have to use here? Chain rule, yeah. So outside derivative times inside derivative. My outside is the parentheses to the 1/3. My inside is the x minus 1. You leave your laptop here. Yeah, it's in the back on that TV stand. Okay, so outside derivative, 1/3 parentheses to the -2/3. Keep the inside intact. Multiplied by the inside derivative. What's x minus 1's derivative going to be? Just what? Just 1, yeah. So, sorry, the problem didn't sound very clear here. It should be x minus 1 to the 2/3 to begin with. So it should be 2/3 parentheses to the -1/3. My bad. It's not very clear on your. So let's clean this up here. Let's get the numerator and denominator to show itself a little bit more clearly. So the 2 stays up top, the 3 is below, and the x minus 1 with a negative exponent will also go below. Now, anytime we want to find critical points, make sure that you consider both the numerator and the denominator, set both equal to 0. Is there anything from the numerator? No, right. If I set 2 equal to 0, that doesn't make any sense. There's no variable to solve for. So we can ignore the numerator. But the denominator has a variable, so we'll set that equal to 0, and we'll find a critical point there. Okay, so if I divide by 3, 0 and divide by 3 is just 0. I can cube both sides as well. I get x minus 1 is equal to 0 till the cube, which is still 0. So x equals 1. So that's a critical point. But is this a valid critical point? And why is it not a valid critical point? And it's not inside the interval, right? So that means there is no critical point for us to test, just endpoints. Okay. So insert them back into the original function. Make sure you do that into the original, not into the derivative. Now we're looking for physical locations on the graph. So plug 0 in for x. 0 minus 1 is negative 1. Negative 1 to the 2/3. Negative 1 squared is 1. Cube root of 1 is still 1. Plug 0. I'm sorry, 0 is 1, right? 0 is 1, sorry. Negative 1 would be negative 1 minus 1, which is negative 2. Negative 2 squared is 4, and then the cube root of 4. Which is slightly more than 1, right? Imagine 3 numbers that multiplies to be 4. It's going to be like 1 point something. So we can consider this as our absolute max, and our absolute min is going to be 1. There's only 2 candidates, so one has to be the max and the other has to be the min. So the way you want to write it is absolute maximum value is cube root of 4, and the absolute minimum value is 1. Okay, so just the y values, not order pairs, not the x value, just the y value. Okay, let's do one more example, and then we can shift over to more quiz review. Okay, so here's our function here. 4/3 x times the square root of 3 minus x on the interval from 0 to 3. There's a square root, but any number between 0 and 3 should be safe. Nothing is causing a negative inside the square root, neither the 0 nor the 3, nor any number between 0 and 3. So we're safe. Our function is continuous. On the closed interval, let's go ahead and make that statement. But this requires a more, okay, so we have endpoints to test for sure. To find critical points, we got to find the derivative. To find the derivative, though, there's a more complicated method to go through. What do we have to go through to find the derivative here? Product rule, okay, good. There's a little bit of what here? There's also what? Inside product rule, we still have. What if I rewrote it? Maybe if I rewrote it, it'll be easier to see. Chain rule, yeah. You got that parentheses with the outside inside portion. Right, so let's see if we can break this up into its components, and then we can find the derivative. Okay, f prime times g plus f g prime. We said there's going to be chain rule here, right? So you got the outside portion and then the inside portion, and we'll take turns with each derivative. So outside's derivative is just power rule. Keep the inside intact. Multiply by the inside's derivative. Negative x becomes negative. Zoom in on this here. So to find critical points, we have to do a little bit of cleanup here. We may need to find common denominators so that we can compress into one fraction so that we can set the numerator and denominator equal to 0. Because right now, this mess is difficult for us to find critical points. So I'm going to see if I can start cleaning up each fraction and seeing what's needed to get a common denominator going. I'm going to do a couple things at once here. So the -1, I'm going to pull that in front because I know that if I multiply all this together, that's going to be a negative number. 4 over 2 is 2. So I'm be left with 2x over 3. And then I'm also going to push that 3 minus x down to the denominator because I have a negative exponent. So I would like to have these two under one fraction, but to do that, I need to do common denominator. So my common denominator is the larger piece here. Is that 3 times 3 minus x to the 1/2. So I need to balance this first fraction. So this first fraction is missing a square root of 3 minus x. I need to multiply the top by the square root of 3 minus x. Square root times square root will just cancel out to be just the expression inside the square root. So 4 times 3 minus x. And this one, there's no changes with the second fraction, so I can keep that 2x here. So this gives me 12 minus 4x minus 2x. So that gives me 12 minus 6x. So my derivative is simply 12 minus 6x up top. And the bottom is 3 times 3 minus x to the 1/2. So now that I have a numerator and denominator clearly defined, I can set both the top equal to 0 and the bottom equal to 0. And I'm going to look for my critical points. So 12 minus 6x, set that equal to 0. I get 2. If I set 3 times 3 minus x to the 1/2 equal to 0, I'll get x equals 3, and that's a duplicate from 4. So I only have 3 critical points to test. I have 2 endpoints, and I have 1 valid critical point, since 2 is clearly between 0 and 3. So how do we test our endpoints and critical points? Where do we plug them back into? Into the what? Good, original, right? So we're done with the derivative. Now we're actually trying to look for the physical locations. So we go back into the original function. And so if I plug 0 into the function here, 4/3 times 0 times anything times 0 is just going to be 0. So f of 0 is 0. F of 3, square root of 3 minus 3 is also 0. So that's going to be 0. 2, I'll get 4/3 times 2, 8/3 times the square root of 1, which is just 8/3. So duplicate doesn't really matter because we only care about the y value. So what's the highest y value that you see? 8/3. What's the lowest y value? 0. It doesn't matter that they're duplicate. They're both a shared y value. So, and we don't care about the x, so we only care about the y. So we can just say absolute max value is 8/3, and the absolute minimum value is 0. Okay, let's see if we can do some review. So in your review packet, page 14, let's do a shadow problem. Okay, street light is mounted on the 15-foot pole. Man is 6 feet tall. So your vertical size will be your constants, and then your horizontal size will be your variables. So we set up our proportion. We can say 6 is to 15. Small height is to big height, as the small base is to the big base. So it's y over x plus y, not x over x plus y. Cross multiply. Clean it up. 6x equals 9y. Find the derivative. 6 dx dt equals 9 dy dt. So the man is walking away from the pole. That means x, as he's walking away, x is getting larger, extending out. So it's a positive 5. So that's dx dt, right? Person walking is dx dt. How fast is the tip of the shadow moving? So we know tip of the shadow is dx dt plus dy dt. If it's asking for just how fast is the length of a shadow increasing, then it's just dy dt. Either way, though, we have to get to dy dt. So we can plug 5 into our equation. Which reduces to be 10 over 3. So dy dt is 10 over 3. So dy dt represents the rate of change of the length of the shadow, but it's asking for the tip. So we're going to add the two rays together. How fast is a person walking? How fast is the length of the shadow increasing? We add those two rays together, and that's going to tell us how fast the tip is moving in relation to the ground. Part B, says find the rate of change of the area. So we got a triangle here. What's the formula for area of a triangle? Yeah. Depending if X is getting longer or getting shorter. So what happens if the person's walking away from the lamppost? Bigger, yeah. So since he's walking away from the pole, we know dx dt will be a positive value. All right, what's the area of a triangle? One half what? One half base times height. So one half base, what's the base of my triangle? X plus y. That's my base. And what's the height of my triangle? 15. Do I need product rule here? No. Because all the numbers can just multiply in front, right? So we can just do dA dt equals 15 halves dx dt plus 15 halves dy dt. So dx dt we already have, which is 5. dy dt we already have, which is 10/3. We add that together, we get 62.5. Area is square feet. Time is seconds. So square feet per second. Right, come look and get your phones. There is homework for 5.1, but that'll be due after the quiz. Tonight, just focus on studying for your quiz. Help session tomorrow morning at 7:15. I'm just going to pick out problems from both packets. I'll send you guys this list, but if you want to take a picture, you can as well. Yeah. Yeah,
I'm sorry, but why is
Great day, guys. Stay for your quiz.
how much that's It's most of not
Yeah. So page 7 and 8 and page 5 on the. Okay, thanks.
I mean, we have like similar pictures like that. Yeah, like I don't.
That's okay.
I was thinking.
I know, I saw like a couple of the game or something.